All right, my good people, I think this will work. Hopefully it is recording and that kind of makes things a little bit better. I don't know if it's gonna work, so we'll see. Okay, so today we're gonna be talking about the scientific method. If you are looking at your Kaplan book, that will be under science, chapter 1. We're going to be focusing on chapter 1 mainly today. Comprehend scientific presentation and use scientific methods, and we will see if there's anything else that we can add into there. Cool? Yeah, exciting. All right. Okay, so the scientific method is, as we go through this, basically modern science is a way of understanding the physical world based on observation, on evidence, on reasoning, and repeated testing. Okay, that means that the scientists explain the world based on their own observation. So does that mean that you look at a chair and you think it's red and it's automatically red, or just because the scientist said so it becomes red? No, it needs to have observable evidence, it needs to have reasoning, and it needs to have repeated testing. So the data that you find on there, you have to go out and prove that this is what you're claiming it is, and you have to make sure that this is repeatable. So if I conduct a study, so if I go out of my way and I do a study, and I gather all the data, well, the next person, if they have the same resources, same elements, everything the same, they should be able to do the same thing and get the same result. That's what makes it repeatable, right? Repeated testing. So with that said, with that, understanding the scientific methods begins with that. The fact that as a scientist's process, it is to observe, to reason, and to test, and to be able to test repeatedly. Sorry. So now we have this section called thinking like a scientist. And a scientist is always trying to find the truth and to discover new things. That's what makes them, they are curious about the world. That's what makes them unique, right? So how can you think like a scientist, right? Thinking like a scientist is based on asking and answering questions, like a little kid. That's what it is. A scientist is almost like a little kid who grew up with the same curiosity and kept that curiosity. Like, do you ever look at something and think, oh, I wonder how this works? Or I wonder, like, why the tides are so high today? Is there a relation to the moon that's there? Is there any connection between these things? So by looking at the world around you, by looking at what you already know, and then starting to ask questions, that's when you begin using the thinking like a scientist and using the scientific method. So you may not know this, but you do this all day, right? You do this repeatedly. You look at things and are like, oh, I wonder how this is working, or is this how this is supposed to be? You ask yourself curious questions, okay? So scientists ask questions and then make detailed observations to try to ask more specific questions and develop hypotheses. So basically what they do is they look at something that they're curious about. And this doesn't have to be science as in, physics, math, chemistry, biology, not just that. It can be science, psychology research also follows the scientific method. So even though it's a social studies thing, it still follows the same ideology. So they look at the world and they think, wow, this is interesting. Let me see what I know about this, and then ask questions, and they develop a hypothesis. And that is an idea of what they think is happening. Okay, so it could be happening that way. It could not be happening that way. They just look at things and see, okay, well, this is what I think is going on. And then they begin to test. And in other words, testing is experimenting. So they begin to ask questions that will then lead to experiments to try to answer their questions and test their hypotheses. Is it a correct thing? Is it a correct conclusion? Or is it not correct? Is there something else that is influencing whatever it is that is causing the subject to behave as it does, right? For example, does the moon have any connection to the tides? It could or it could not. So someone went out and tested that and they realized that, wow, okay, no, there is. Every time this happens, the waves are this big, or however it works, right? I'm not totally familiar with that. But the concept is that leads them to question what they have and to see if this is correct, and to make sure that they don't manipulate the results in their favor. So they're not biased towards their own hypotheses. Yes, they would hope that it's true, but if it's not true, they may stumble upon something else. Because a scientist seeks truth. That's the first thing they look for, yeah? So from the results of their experiments, scientists draw conclusions, right? Conclusions are what they think at the end, and a conclusion describes what the evidence tells the scientists. So they don't just go off the top of their head, they ask questions, they do an experiment, and based on the result, they have an answer and they share that answer through the conclusion. So all knowledge comes from the process of scientific investigation. So that curious process, that testing process, that experiment process, it all comes from scientific investigation, and these are shaped by the scientific method. Which leads us to ask, what is this scientific method? So a scientific method is a process used to investigate the unknown, kind of like what we were talking about. There's a curiosity there. Why is this that way? Is there something I don't know? It's almost like you're looking for the truth. It is a general process of scientific investigation. The process uses evidence and testing. So again, they have to stop, they have to look, they have to investigate, they have to make sure that this is repeatable and so forth. And scientists use the scientific method so they can find information that they are looking for. And a common scientific method, or a common method, allows all scientists to answer questions in a similar way. So by having a certain structure, by having a definite structure, then the scientists all over the world, any scientists all over the world, will use that same way, which means no matter what language, no matter which country the scientific experiment is being conducted, it's being had, it doesn't matter, they will end up with the same process. So I can pick it up from a journal from India, which is across the world, and still find the same format for everything. And that makes it easier and more unifying to share information throughout the world. Okay, so what are the steps for scientific method? Well, 1, you make observations. 2, identify a question you'd like to answer based on that observation. 3, form a hypothesis. 4, test it. And 5, analyze your results, draw conclusion. And lastly, you communicate the results, right? So whatever it is, good or bad, you share it. First and foremost, you make observation. So imagine that you are a scientist, and while collecting water sample at a local pond, you notice a frog with 5 legs instead of 4. That's weird, right? So you're like, yeah, that's interesting. Let me think about that. It will arouse your intellect, right? Regardless of whether you are to carry out why or whatnot. If you see a 5-legged frog, you're gonna be in shock. You're like, this is so weird, right? So then, as the scientist in the local pond, you start to look around and you discover that there are a lot of other frogs that have extra limbs. So there are 10 of them, right? There are 15 of these frogs everywhere that have 5 legs instead of 4. So one frog even has a limp coming out of its mouth. These are your observations, or the things you notice about the environment using your five senses. Okay, so what you saw with your eyes, maybe you touched the frog, maybe you noticed a smell in the air. These are all observation, right? Using your senses to make sure, to make a conclusion or to understand what's going on. Yeah? Sweet. Step 2 is identify a question based on your observation. Naturally, if you find all these frogs and they have limbs coming out, you're probably going to think, why are they so deformed, right? Why are there so many deformed frogs, right? That's basically it naturally. So follow that natural process. Or maybe your question is there something in the environment causing this defect, like water pollution? Because it's not natural for frogs to look like that. So you wonder. And when you wonder, you start asking questions and you start looking for answers. And that's part of the scientific process. And you don't know if this large number of deformalities is normal for a frog. So what if many frogs found in the pond and lakes all over the world have the same deformities, right? What if there's a lot of frogs that are like that, but you just don't know it? So what do? You then, before you look for causes, you need to find the number of these kind of things or deformities is unusual. So you need to look for information. So you know what you have, you ask questions, you try to find, you try to look for it, and you try to wonder why. But most likely it's a frog, so it has 4 legs. So you start asking the questions. So besides finding out why the frogs are deformed, you should ask, is the percentage of deformed frogs in this pond greater than the percentage of deformed frogs in other places? Still, we are in the question phase. We haven't looked for information. We haven't asked for anything. We are just asking ourselves questions and thinking, okay, how do I need to proceed, or how can I proceed to find the answer? Step number 3 is conduct a hypothesis. And so a hypothesis is proposed explanation that tries to explain the observation. So it kind of looks at what you have, what you've already looked at, and you come up with a conclusion. What you think is causing the frogs to be deformed. And in this case, you can ask, so a good hypothesis allow you to make more predictions. For example, you might hypothesize that a pesticide from a nearby farm is running into the pond and causing the frog to have an extra leg. If that's true, then you can predict that the water is a pond of non-deformed frogs that will have lower levels of pesticides. So if you look at the pond, if you are looking at it and you see these frogs and you know that there is a pesticide, a farm nearby, you're like, okay, maybe the pesticides, which is like the little bugs on the farm, got into the water and got into the bugs, and that's what's causing them to be deformed. In this case, if that's true, then you can predict that in the pond, there are non-deformed frogs that will have lower levels of that pesticide. So you're thinking, okay, if the pesticide is causing it, then the frogs with a higher level of that pesticide is going to have an extra leg, and the ones that have a lower level should be fine, right? If that's your hypothesis. So that's a prediction you can test by measuring the level of pesticide in 2 sets of ponds, those with deformed frogs and those with nothing but healthy frogs, right? So the hypothesis, basically, you think, okay, if I do this, then the results should be this, okay? Then you set out to do that. So in this case, every hypothesis should have the following, right? It needs to be written in a way that can be tested using experiments to collect evidence. So the pond situation, that's something you can test. Pesticide, you can measure that, okay? It has to be able to be proven wrong. It has to provide measurable results and provide yes or no answers. Okay? So in our example, or let's look at the example here, it says the number of deformed frogs in the pond that are polluted with chemical X is higher than the number of deformed frogs in ponds without chemical X. Cool? So if the frogs, if pesticide is causing the frog to have an extra limb, then the pond with the frogs with the extra limb should have more pesticide and the other ones should not. Okay, and that's testable. Yeah, does that make sense? Any questions? All right. Number 4, you want to test your hypotheses. So to test the hypotheses, you need to design an experiment. An experiment basically is a test, right? And you design it in a way that is that's coherent with what you are trying to prove, right? Or prove right or prove wrong. It has to be designed in a strategic way that answers that question, and you can manipulate the factors that are in it so that it's not wrong. So you could count the healthy and deformed frogs and measure the amount of chemical X in all ponds. The hypotheses will be either true or false. Very simple. This experiment is very simple. You have the pond with the deformed frogs, find a pond with healthy frogs, count how many frogs are deformed, count the healthy frogs in the other one, and then you can see the level of pesticide in either one. Then you can measure the level of pesticide in the water. Yeah? So simply put, you design an experiment that is intended to answer your question very strategically, okay? Very purposeful. So you have to have a purpose of why you are doing everything that you are doing in the experiment. Cool? Awesome. All right, step 5, you analyze the data and draw conclusions. So if hypotheses and experiments are well designed, the experiment will produce results that you can measure, collect, and analyze. So you need to be able to look at the numbers, you need to be able, or information, you need to be able to collect it, and you need to be able to analyze it. If something is not measurable, then it's not part of the scientific, it shouldn't be a part of the scientific method because there's no way of actually measuring this. Yeah? Of course, there are quantitative and qualitative answers, but those are different. You do have a scale of some sort. All right. So the analysis should tell you if the hypothesis is true or false. Let's take a look at the at this data set. Okay. So what do we have? In the first column, we have polluted ponds. In the second one, we have numbers of deformed frogs. In the third one, we have non-polluted ponds and number of deformed frogs. So in the first pond, okay, so pond number 1, how many frogs were deformed? 20. This is the polluted pond. In the second one, 23, right? No, that's number of ponds. So for this one is polluted pond. This is the non-polluted pond, right? So we have to keep track of what is this heading. So they took and tested 5 ponds and they counted how many deformed frogs are in each. So in the first one that is polluted, they had 20. In the first one that is not polluted, they had 23. In the second one that has 23, and the second one that is not polluted has 25. So looking at the data, do you think the hypothesis is correct or incorrect? It's incorrect. Why is it incorrect? Right? Exactly. So this, you can say that this hypothesis was actually proven incorrect. So let's keep going, right? Because the data, so while they went out, they did everything, and you think, oh, I want to be right. but that's not it. That's not the goal. The goal is to find the reason and to find the truth. It's not about being right or wrong. So if you're right or wrong, it's irrelevant in this case, so long as you know and find the truth. So your results show that pesticide level in the two sets of ponds are different, but the average number of deformed frogs is almost the same. Your results demonstrate that the hypothesis is false, and the situation may be more complicated than you thought. That gives you new information that will then help you decide what to do next to better understand what's happening to the frogs and why. So maybe you start the scientific process all over again and look for different reasons, okay? So step number six is to communicate your results. If the hypotheses and the experiments are well designed, the results will indicate whether your hypothesis is true or it's false. A scientist will then communicate the results to others in the scientific community so that other people who are testing the same thing don't make the same mistake, okay? Or don't replicate the process and have it be incorrect. Maybe they want to replicate it and think, oh, if I change something, maybe I'll get a different result, okay? So doing this allows others to review the information, do another investigation, or understand a problem better. In most cases, scientists will write a report and publish it or present it to others. More often than not, it is presented in a scientific journal. And a scientific journal has a lot of scientific research that is usually up to date with what is going on in whatever field they are in. Cool? Awesome. So that's it for that portion. Let me do this. Okay.